Hello, good day everyone. We are here once again for another interesting lesson in science. In today's lesson, we are going to deal with the reflection of light in spherical or curved mirrors. So, if you're watching this, just sit back, relax, and enjoy a moment of science with Surabin. In this lesson, we will deal with the reflection of light in spherical or curved mirrors. The objectives of the lessons are the following. We will identify the different types of spherical mirrors, and we will also describe different image characteristics formed by each type of spherical or curved mirrors. And lastly, we are also going to give or cite some practical applications in each type of spherical or curved mirror. So, without further ado, let us now begin with our lesson for today. First thing that we would like to deal with in this lesson is what is specifically a spherical mirror? So, a spherical mirror is actually a type of mirror with a curved reflecting surface, and that both of its surface, whether the inner or the outer surface, can actually reflect light, meaning to say they can actually project or form images. And based on the shape of their curved surfaces, they are actually classified into two. We have the concave and we have the convex mirrors. So if the reflecting surface is actually on the inside of a sphere or a circle, then we refer to it as a concave mirror. But if the reflecting surface is on the outside of a sphere or a circle, then that is a convex mirror. Okay, so to give you an easier understanding about these two types of spherical mirror, we can have this schematic diagram you see right now on the screen to simplify our version of concave versus a convex mirror difference there. Now, as what I've said, different image characteristics can be formed depending on the shape of the curved surfaces in each type of spherical mirror. So what are exactly the differences between the image that are formed in these spherical mirrors? First, for concave, it's actually called a converging mirror because it is used to focus light rays or to concentrate light rays. And because of this, the image that are formed in this type of mirror actually varies depending on where the object is placed in front of the mirror. Now, the image can be small or they can be enlarged, they can be a real image or they can be a virtual image, or they can be upright or they can be an inverted image. That's usually the characteristic of a concave mirror. In contrast, for convex mirrors, they are called as diverging mirrors because they diverge light rays or they scatter light rays. And in this case, the image that are formed by convex mirrors are always smaller and virtual compared to the object. So those are the main characteristics and differences between these two types of mirrors in terms of their image characteristics. So, how do we usually describe the images formed by plane mirrors? So, we will deal here in this lesson the ray diagram method. Now, what is a ray diagram? A ray diagram is actually just a diagram that traces the path of light rays, or it takes the path of light in order for a person to view a point on the image of an object. So, what does this mean? It simply utilizes the path of light rays as it enters the mirror, and then we just trace it so that we can make predictions on where the image is actually formed and how is the image characterized. So, before we go there, let's first identify the different parts of the spherical mirror because it will help us understand further when we do our construction of ray diagram. So let's go with each part. So we have the radius of curvature, which is labeled R in the diagram, which is exactly the distance between the vertex and the center of the curvature, which is point C in this case. Now, I want you to think of a mirror as once a part of a sphere or a circle, and that when we get a segment or a portion of that sphere, then we basically have your curved mirror. And the radius of curvature actually corresponds to the radius of the sphere or the circle itself. Okay? And we have the focal point or F, where this is the point at which reflected rays will meet. That is actually halfway the distance between V and C in your diagram. And we also have the focal length, which is half the distance of the center of curvature. Or we can also say it in another way, that it is the distance from V to F, the big letter F of your mirror, which corresponds to the vertex and the focal point or focus respectively. So, next is we have the principal axis, in which that is the imaginary line from the center of the mirror. The one that you see as a vertical line there labeled with P, that is your principal axis. And then we have the vertex, which is your V, which is the center of the mirror. And we also have the center of curvature, in which this is actually the center of the sphere in which the mirror forms a section. So, in short, this corresponds to the center of the sphere where the mirror was once a part or portion. Okay? So, we need this information in order for us to execute properly our ray diagram construction. Now, when we describe images, we usually employ what you call as the lost method. It's just actually an acronym for L, which stands for location, where the image is actually formed. And usually we use the points F and C, which corresponds to the focus and the center of curvature, as our reference to where the image is formed. And aside from this, we also utilize the positioning of the images above or below the principal axis. Later on, we will be able to clarify all these things once we do the ray diagram construction. Then O stands for orientation, wherein it could be of two types. It could be inverted or an upside down image, or it could be an upright or erect image. So when you say inverted, you can also say that it has a different orientation from the object, while if it's upright, then it has the same orientation as that of the object. Now, let's go for S, which stands for size or magnification. Now, when you say magnification, that means how big or small the image gets in front of the mirror. So it could be enlarged or bigger than the object. It could be reduced or smaller than the object. And it could be of equal size or the same size as the object. And last but not the least, we have T, which stands for the type of image. We can only have two types of images. That is, it could either be real or it could either be virtual. So when you say real image, that means it is an inverted image that's formed when light rays meet at a particular point after the reflection from the mirror. So usually, a real image is always inverted. Okay? And a virtual image is an upright image formed when the light rays appear to meet at a definite point after reflection from the mirror. So this means that a virtual image is always upright. So they are always in pair. If a real image is formed, then expect that the image is inverted. And if the image is virtual, then expect that the image is also an upright one. Now, let's move on to the ray diagram construction in each type of curved mirrors. So first, let's start with the concave mirrors. Now, I have here a diagram that corresponds to the parts of a sphere or the mirror and as well as a concave mirror. Now, there are actually three rules that you need to remember. There are other rules that you can see or you can search around the internet about the construction of ray diagram, but in this lesson, to make it simplified, let's just use three rules in constructing ray diagram formation. And these are the following. So I want you to follow this carefully because this is very important. Now, the first rule, it says that light rays that leave the object, which is the upward arrow, in this case in the diagram, parallel to the principal axis, which is your point or your P, are reflected and pass through the focus. So how are we going to interpret this thing? So light rays leave the object parallel to the principal axis. So you always start, in this case, since my object is an arrow, I always start from the very tip of that object and then follow the rule as it says that it will always leave the object parallel to the principal axis. So I will have to draw a parallel line from the tip of the object towards the mirror. Okay, so it should hit your mirror surface because after it hits the mirror, it is now reflected and passed through the focus. So how are we going to execute that one? So just draw a straight line from the point where the parallel light ray struck the mirror and then let it pass through the focus of your curved mirror. Okay? And that is how we execute rule number 1. Now let's go to rule number 2. Rule number 2 says that light rays pass through the focus or F and are reflected parallel to the principal axis. So once again, how do we interpret this? Again, you always start at the tip of the object, in this case, the arrow. Okay? So according to the rule, that light rays need to pass through the focus of your mirror. So we will just draw a straight line passing through the focus from the tip of your arrow or the object in this case and let it strike the mirror. Now, what happens when it strikes the mirror passing through the focus? Now, according to the rule, they are reflected parallel to the principal axis. So, I'm going to mark the point where my light ray has struck the mirror, and after that, I'm going to reflect it parallel to the principal axis. Okay? So you notice that my reflected light rays are denoted always with a dashed line so that we can easily trace where the image is formed afterwards. So this is how we interpret rule number 2, and let's inject rule number 1 in this case so that you will know that this is now how my image or ray diagram formation should be like after following the first 2 rules. Okay? Now, let's move on to the third rule. Okay? According to the third rule, light rays should pass through the center of curvature, or your C, will strike the mirror at right angles and will be reflected back to its path. So, what does this mean? This means, class, that every light ray that enters the mirror and passing through the center of curvature, they will always be reflected back to its path. Meaning to say, the reflection is towards the same path the light rays or the incident light rays have taken when it hits the mirror. So how do we do this? So all we need to do is just draw a straight line passing through the center of the curvature. And according to the rule, it will always be reflected back to its path. That's why I drew a dashed arrow to indicate that it lies on the same plane where the light rays have traveled towards the center of curvature. Now, that's how we interpret rule number 3. Now, why do you think there is a blue arrow there? Now, let's try to inject rule number 1 and rule number 2 from a while ago. And you will see a common point where all these reflected rays have intersected. And as you can see, all the light rays that traveled from the object from rules 1 to 3 have intersected at this point. Okay? So this point indicates where the image is formed, indicated by the blue arrow. Now, we know already where the image is located. So we can now start describing how should we characterize this image form. So, as what we discussed a while ago, we will follow what we call as the lost method, wherein L stands for location, O stands for orientation, and that S stands for the size, and T stands for the type of image. So, let's employ that. So as you can see, I'm using the lost method here, wherein the image first location is between F and C because it's exactly located no? Midway or midway between F and C, right? And next we have the orientation. It's inverted. So why do I know that it's an inverted image? It's because my intersection happens below the principal axis. And since below the principal axis, compared to my object, it will be inverted because it's found below the principal axis. Okay? That's why I know it's inverted. But if the intersection happened somewhere above the principal axis, then it will not be inverted anymore, but it will be an upright image. Now, next is reduced. So how do we know that it's reduced? So we can just make a quick comparison by just looking at the relative sizes of the blue arrow and the black arrow in this case. Okay, and you will see that the blue arrow is actually smaller compared to the object, which is the black arrow. And in order for us to verify this, you can actually do some calculations using mirror and magnification equations, in which that is not part of our discussion for this afternoon or for today's lesson. And we have type of image. It's a real image because it's an inverted image. An inverted image are always real image. So this is how we are going to construct ray diagram for concave mirrors. Now, let me just tell you about these image characteristics of concave mirrors through ray diagram formation. As mentioned a while ago, image description varies with the object position from the mirror for concave mirrors. As seen by our illustration there, one girl places her hand in front of the mirror, it becomes bigger. But as you can see, a man standing in front of the mirror here appears to be inverted. So that's what I mean, that wherever the object is placed in front of a concave mirror, image characteristic actually varies. And that's what we are going to deal with in our next lesson. So for the meantime, let's move on with the convex mirrors. So how do we apply ray diagram formation for convex mirrors? Actually, the rules are not changed. It will always be the same and true for convex and concave mirrors. But how do we execute ray diagram construction for convex mirrors? So once again, let's start with rule number 1. That all light rays parallel that enter the mirror parallel to the principal axis are always reflected, so they appear to come from F behind the mirror. So how do we do this? So light rays that leave the object parallel to the principal axis, just draw a straight parallel line there. Let it hit the surface of the convex mirror. And once it hits the convex mirror, it is reflected away from the mirror so that it passes from F behind the mirror, so that it seemed to pass from F behind the mirror. So that's how we interpret rule number 1 in this case. Okay, so let's move on to rule number 2. that all light rays directed towards the focal point are reflected parallel to the principal axis. So how do we execute this? So first, just draw and trace a straight line that passes through the focus. Okay? I intentionally made a difference between the arrow's thickness here because I want you to understand that the arrows represent the light rays that enter or strike the surface of the mirror. But here in convex mirror, because the reflecting surface is on the outward of the sphere, you need to understand that it only hits at this point. But we just trace it so that it seems to pass through F from the mirror. Okay? But in reality, it only strikes this portion here. But we just trace it so that it seems to pass through the focus of your mirror. Now, what are we going to do right now? Straight towards the point where the light rays struck the mirror. That's the point where we start reflecting our rays parallel to the principal axis. So, as you can see right now, I just simply identified where the light rays struck the surface of the mirror, and from that point, I reflected my light rays parallel to the principal axis. So, and let's go back and trace rule number 1 again. And you can see this is how your ray diagram construction should look like. Okay? And let's move on to rule number 3. Wherein light rays that passes through the center of curvature will strike the mirror at right angles and will always be reflected back to its path. So what do we mean by this? So just simply draw an arrow or a light ray that seems to pass through the center of curvature of your mirror. And as the rule says, it will always be reflected back to its path. So that's how we trace rule number 3. And injecting all the previous rules applied a while ago, from rule number 1 to rule number 2, you can see that the reflection of light rays are actually happening behind the mirror, specifically at the point where the blue arrow is being projected right now. That indicates where the image is formed. The intersection of the reflected rays, in this case, the dashed lines. Now, how do we describe the image formed here? Now, again, we use the lost method, wherein it's behind the mirror, the location. Why do I know it's behind the mirror? Because it's located on the opposite side of the mirror. And it's upright because it has the same orientation as the arrow or the object. And how do I know it's upright? It's because the intersection of the light rays happen above the principal axis. So that's why I can say that it's an upright image. And of course, it's reduced. It's reduced. And just look at the comparative size between the black arrow and the blue arrow. And you will see that it's really getting smaller. And of course, the type of image is virtual, because virtual images are always upright image. And that's how we follow ray diagram construction for convex mirrors. And unlike concave mirrors, the characteristics of the images formed by convex mirrors are always behind the mirror, they are always upright, they are always reduced, and they are always virtual. Okay, so if you stand in front of the convex mirror, you will always appear to be smaller compared to your actual size. So how do we benefit from these image characteristics formed in each type of mirror? Well, actually, they are used in several practical applications, like the ones that you see as your rear view mirror for vehicles, or even the sidecar mirror for vehicles. They are actually convex mirrors. And they are usually used because convex mirrors reduces the size of the image so that you can have a wider view And the reason or the purpose for that one is that you can see an approaching vehicle coming from behind. And even in blind curve roads, we attach a convex mirror so that we can easily see an approaching vehicle from the other side of the blind curve. And usually the most common application of convex mirror is the one that you see in the convenience stores. Very big convex mirrors. It's used for security purposes, right? So how about for concave mirrors? Well, you see your headlights in your cars, your vehicles, your flashlights. They are actually embedded with it a curved mirror which is of concave type because without it, it will not shine brighter. Okay? And the dental mirrors, wherein dentists use this to view your defective, I don't know if the right term is it defective or your problem tooth or teeth, right? And even in astronomical observations like for telescopes. Usually, in the earliest times, um, scientists employ the use of lenses, but there are problems with lenses. Number one is that it's a very tedious task to create a lens of bigger focal length or higher focal length, and at the same time, it experiences problems like chromatic aberrations. Like it's also very hard and very expensive to create one. So that's why avoiding these problems, um, most of the astronomical telescopes nowadays are utilizing reflecting telescopes because it answers the problems of chromatic aberrations in lenses. And in fact, the biggest telescope, which is the Hubble Space Telescope, is made up of reflecting mirrors, which are concave ones. And those are actually practical applications of lens of mirrors, okay? And actually, this is now the end of our lesson for this day. So those are the different image characteristics of spherical mirrors, concave to convex mirrors. So to recap, there are two types of spherical mirrors. We have the concave one and the convex one. And each of these types of mirrors have different image characteristics depending on where the object is placed in front of the mirror. And we employ a ray diagram method in order for us to qualitatively predict and describe the images that are formed in each type of mirrors. And that's actually the end of our lesson for today. So I hope, guys, that you learned something out from our discussion for this lesson. So if ever that you have some questions or some clarifications regarding the concept that has just been shared to you, please just message me through my messenger account. You search Marvin Earl or Rabino, or you can email me at mreinsteinlove@gmail.com. I will post my contact information in the description below, so just refer to it later. So thank you so much, and I hope that you have enjoyed and learned something out from our discussion for today. This is Mr. Rabino saying, spread love, spread science, spread knowledge, and enjoy a moment of science with Sir Rabino. Bye!